Welcome. In this video we want to talk about how gas is accelerated through a rocket nozzle. So let's do a bit of a reminder. Rocket nozzles take on this converging, diverging shape that usually have a circular cross-section, the area of which changes as you move along the length of the nozzle. We're going to draw the direction of the exhaust flow in the positive x direction. What we have in a rocket nozzle is we have high pressure, low velocity gas at the entrance end and low pressure, high velocity gas at the output end. And the goal of this section is to try and find out how the gas is actually accelerated through the nozzle. To do that, we actually need to look at a small slice of gas. So I'm going to choose some arbitrary slice right here. I'm going to redraw this slice down below, but I'm going to put some thickness to it. So it's going to happen at some position x, and the slice is going to have some thickness dx. Now, at this position, this slice is going to have some cross-sectional area, A, and the slice is filled with the exhaust gas, and the exhaust gas will be at density rho of x. Finally, we have pressure pushing on the gas from each side. So we're going to have a pressure pushing from this side, which we will call P of x, and we're going to have a pressure pushing from this side, which we're going to call P of x plus dx. Our goal is to find out how this pressure, the pressures on the two sides, accelerate the gas. The way we do that when we want to look at accelerating motion, we need to use Newton's second law. Newton's second law reads that the net force on an object is equal to the mass times the time change in the velocity, or the acceleration. For us, we can just start identifying what these are. We have a pressure. We have a pressure P of x. We have a pressure pushing in the other direction, P of x plus delta x dx, times the area. This is the two forces that are acting. We have a force from this direction and a force from this direction. The mass can be found by looking at the density, rho, times the volume, which is the area, times the thickness, dx. That's the volume of that small slice. Finally, we're going to need a little trick here. We have here u as a function of time, but everything that we know in the system is going to be as a function of position x. And so we want to rewrite u as instead of as a function of time, as a function of x. To do that, we're going to use the chain rule. We're going to rewrite du dt as du dx times dx over dt. But now we come to something that's kind of neat. dx dt is the change in position and change in time. This is simply the velocity u of the gas. So now we can simplify the system and reorder it slightly. There's area on both sides, so we can cancel those. I'm going to take this dx, I'm going to move it to the other side. Should have been parentheses there. I'm going to move this dx to the other side. This is going to give me, and I'm going to factor out a minus sign here. So I'm going to get minus p x plus dx minus p of x, whole thing over dx. This is going to be equal to rho u du over dx. But we should recognize this. This right here is a derivative. It's the spatial derivative of the pressure with position. And so we can write this as minus dp dx is equal to rho u du over dx. And so at this point, we've done some mathematical manipulations, and we have a relationship that we can use to further understand the system that we're looking at.